Hey everybody, I want to just do a quick overview of torque. We've actually talked about torque, but we've talked about torque in a linear manner. I want to talk about torque related to a rotational manner, okay? Let me get to more of my video, okay? And get in the stream of things. Oh, there's my cute dog. My Grace. Yep. Gratuitous puppy shot there. Boy, I still can't see myself in these things. Well, maybe you don't need to see me, let's be honest. So in the past, we've had torque, and we did this right before Christmas break. A torque, right, had a radius and a force. Now, I could not find anything to hang, so we're hanging Legos, right? And we know, as far as if I have this torque, right, or if I have this force hanging from this ruler, right, the amount of rotation I need to keep it level, right, is greater, right, than if I put it here. It's a lot easier to keep that level. It's a little bit of center of mass, right, and so on. So if I move the mass out, right, much harder to keep up. You can also use that in levers for mechanical advantage and such. So the equation, right, the equation was a radius times a force. Now I'm not sure if you are recognizing a pattern, right, and they had all this force perpendicular and stuff like that. So if I wanted to find, I have my radius, I would sit there and find my force perpendicular and do the product of those to get the torque. But I don't know if you see this relationship. For instance, if I wanted my velocity and I had my omega, I'd multiply it by r, right? Omega being my angular velocity, I'd multiply it by radius. If I wanted my tangential acceleration, I'd find my angular acceleration and multiply by r. If I wanted my arc length, or the distance traveled, I'd take my angular displacement times r. So if I am taking force and I multiply it by r and I get torque, when it comes to rotation, there's a rotational equivalent of force on an object in a linear manner and a torque on an object in a rotational manner, okay? So let's see if we can make that correlation. When I apply a force to an object, and I had a net force, right? What would happen to my object? If I had a net force this way, and it overcame friction, it overcame structural resistance, I would have acceleration. So now, what if I had, right, a wheel? This is a little bit harder. And I apply a force, right, perpendicular to a radius. What do I get? I get an angular acceleration, okay? Are you kind of getting that? Are you kind of getting that? So in a linear mass approach, a net force causes acceleration, but force times a radius gets us to a angular quantity, right? An angular quantity, this connection where now I can multiply my force times my radius here, right? Force times my radius here, and I can get my torque. I know there's a little bit, that's a little bit wanting and longing for that, because normally we go angular times radius to get linear, and I know I've got linear radius to get torque. So it's a little different. But if I want to get angular acceleration, and I've got, I don't know why I have all these strings. I think I was going to hang that Lego thing from it, but I don't need to do that, right? If I apply my force at a smaller radius, I get less angular torque, right? If I apply the same force on the outside, I get a greater rotation, okay? So ultimately, this unit is about torque, but it's going to be torque related to something rotational. And if I have a net torque, right, just like I'd have a net, right? So if I have a net torque, right, and I'm going to have some sort of mass and some sort of acceleration, we'll have to talk about that. That net torque, right, if I have a net torque, I'm going to have some sort of angular acceleration. So which way wins if I've got this scenario? I've got force 1 and then force 2 is 5 times force 1, right? They're going to counter each other, except this has 5 times as much. So my net torque, right, is basically 5F1 minus F1, right? So 4F1 is my net torque. And when I say that, we can calculate those torques. They will have the same radius, right? But ultimately, 4 times as much, I'm going to get rotation in the clockwise direction. So the plus and the minus related to clockwise, counterclockwise. Either way you set your frame of reference as far as positive and negative. So that should get you ready for torque related to rotation. Okay, this is the past. This is what we're doing currently. So ultimately, the thought is there's a net torque, there's going to be a net acceleration. And so if we've got force net equals mass times acceleration, we're going to get to a net torque. And we've got to figure out what the equivalent for mass is. And we should have an equivalent for acceleration. So I'll just stop it there as my intro. That should be enough to get you into your homework. And I'll make sure there's some support videos identified in that unit. Okay, so basically your assignment is to work through the 3 homework problems. What is it, 22, 23, and 22, 24, and 25, I think. So just check out that worksheet. So I'm gonna shut her down, and I hope that works.